Welcome again to electrostatic fields. In this video, we'll discuss Stokes theorem and second Maxwell equation. So Stokes theorem mentioned that the line integral of a vector over a closed loop, this part, equal to the surface integral of its curl over the bounded surface. This one. What is here is called nabla cross f, which we call also curl of f. If we equate these together, we get this formula. Integration over the closed surface f dot dl equal to double integral over open surface nabla cross f dot n ds. The curl is a vector operation which tells us how the field rotates or sphere. If we look to the curl as a block diagram, it is a block diagram, whatever is called curl. It has input as a vector field. It has output as another vector field, here f, here nabla f, and it can be calculated based on the coordinate system we can apply to Cartesian, cylindrical, and spherical. Here we derive together the second Maxwell equation in the case of electrostatic because this equation is not the same for electrodynamic. Anyway, let's focus here in electrostatic, and we start with the equation V equal to the integration of E dot dl, and we don't forget the minus sign. This is the correct equation. And if we say this is for AP, then integration from A to B. Now let's imagine that we are moving from point A and just go some curve and return to point A. In that case, this is a closed curve, and we started and returned into the same point. So this one become A. This means this is VAA, which is just zero, like this, because we started and ended into the same point. This means integration of E to dl equals zero if we make integration over a closed curve, and this is the integral form of the second Maxwell equation. To derive the differential form, we will use or apply the Stokes theorem, which we have just learned. We have E dot dl based on the Stokes theorem, if it was over a closed curve, equal to the curl of this E multiplied by dot dn and integrated over the surface. And at the end, this will equal to 0, as we have proved here. This means that since E is not 0, but the curl can be equal to 0, then we can claim that curl E for electrostatic field is equal to 0. Just for your reference, in electrodynamic, this value will tend to be minus p by partial p by partial t. Anyway, this is not important for now. And one last note is that for electrostatic field, if you are, for example, given a field and you are asked whether this field is electrostatic field or not, you can use the curl relation, and if at the end you got curl E equal to 0, then this proves that this is an electrostatic field. Let's conclude by one example. We are given a vector E like this, and we have here actually two things to do. First one is show that this function can represent an electrostatic field, and second one, find the corresponding volume charge density. To do so, let's do the first one. First part, for a function to be an electrostatic field, it must satisfy nabla cross E equal to 0 or curl E equal to 0, and this we have said for the electrostatic field it has to satisfy this relation. And this is how to calculate the curl in Cartesian coordinates. IJK just the direction. Then we take every component down here. If you check carefully, just these three components, this one is fx, this one is fy, and this one is fz. Then we need to apply the curl. To do so, this become positive, negative, positive. If you want to calculate I component, just erase these two things, make cross multiplication like this, and don't forget the negative sign here. If you do so, partial y for this function, this constant for y, then you need to have here differentiation of y squared, which is just 2y. 2y multiplied by 3x squared is nothing but x squared y. Then we do the opposite. Negative here come from this negative, and partial for this function, this part is nothing but the constant for z. Differentiation of z is just 1. Then you are left with 6x x square y. Then we do the same for j and k component like this, for example. So here you differentiate for x. You have x squared, it becomes 2x multiplied by 3, it becomes 6x, and y squared is also constant for x. Then you do for z, don't forget the minus sign here. You have here minus sign. Partial z for this one is nothing but 6xy squared, and differentiation of z is just 1. And of course, this because all of these are nothing but constant for z. Likewise, you can do for k, but don't forget that this part is positive. If you check here, you'll find this is equal to this part, then it's 0. Same here, same here. So all of this quantity will equal to 0, means curl E or nabla cross E is equal to 0. Then we have proved that this one is electrostatic field. The second part, we are told to find the corresponding volume charge density, and this simply nothing but Maxwell first equation in a differential form, because divergence of D equal to rho V. Then we just apply the relation between D and E, D equal to epsilon E, substitute in this equation. Then you can get that epsilon div E equal to rho V. And finally, U rho V can be calculated using this equation. Then we need to find the divergence of E in order to find rho V. So this is how divergence is calculated in Cartesian coordinate. Just you take every component, differentiate it with respect to the direction. If it was a x component here, just differentiate in terms of x. Y component, differentiate in terms of y. Z component, differentiate in terms of z. This is what I am doing here. If you do so, it's very simple differentiation. You have here 6xy squared z. All are constant. 6 y squared z and 6 are constant for the x derivative. You have here only x, which has derivative of 1. Likewise, have here 6x squared yz. Here only this one is a function of y, which means its differentiation is just 1, and the remaining part will come here. And finally, there is no variable here, it's just all are constant in terms of z. Then you will have differentiation as 0. Simplifying this, you can by substituting in the equation which we just find, then you can get that our rho v equal to 6 epsilon x squared plus y squared z. Thank you.